Good afternoon. As she said, my name is Laura Hinkelman. I'm a solar PV performance consultant at Black & Veatch, and I'm going to be speaking about using CAD output files for terrain losses in PVsyst. And before I get too far underway, I wanted to acknowledge the rest of our team. In particular, Stephen Sherwood did all of the PV case work for this, and Saurav Kadel did the majority of the PVsyst runs. So a lot of people have come up here and said that solar projects are getting more and more complicated, the terrain's getting more complicated, et cetera, et cetera. I'm not going to belabor that point. I'm going to try to propose a potential solution of how we can do some modeling that will incorporate those effects. So in particular, I'm going to use 3D scenes that are output from CAD, CAD systems as input to PVsyst. And in particular, we're using output from PVcase as a front end to the CAD system. The general outline is I'm going to first review slope effects and then show how you can use PVcase to create a shading scene that includes 3D topography, and finally discuss some of the benchmarking work we've been doing using these scenes. And I'm going to get some water. So this is probably a review to people, but this is an illustration of what happens when you have trackers on east-west slopes. You have standard backtracking, so no terrain adaptive backtracking. So you have your nice backtracking. You hardly ever have, you don't have shadowing on your modules. But if you have slopes to the east and west direction, these the trackers on the far side of the hill are effectively closer together, which causes increased shading. And the trackers on the near side of the hill are effectively farther apart. So again, there's no shading. And we like to point out, because we've had people make comments about this, the slope effects in the east and west directions do not cancel each other, because the only thing you can get is shading. You can't get less shading when you already have zero shading. So there's never an improvement, there's only ever a loss. The north-south slopes are simpler to think about in the direction of the trackers. They're not as critical as the east-west slopes, only causing slight losses or gains. And in this case, they do cancel because you get a loss on one side and a gain on the other side. I'm going to go through a review of PVcase ground mount. This is not the yield tool that was discussed yesterday. This is the ground mount tool that is the front end to a CAD system, and some design groups are already using this. And I know ours were, so this was an easy transition. So in PVcase ground mount, you're able to bring in the features from the CAD, and then that would include things like the project boundaries, the wetland delineation, and so forth, and then do a layout automatically for the shape of your system, your project. And there's no pointer, is that right? So most of the sidebars and toolbars you see there are actually from the CAD system, but the top one is from the PVcase. So this is a close-up. You can see what they look like. You can see the individual trackers. You can see the inverter pad there and the roads and so forth. So this has already been put in by our designer. And then the next thing to do is to bring in the terrain, which makes use of the geolocation information that is already in your CAD file. So it knows where you are. And then there are a variety of DEMs that you can use. Pick your favorite, and then the PVcase will create a surface mesh and conform the existing objects to that mesh. And the mesh is in there, but it's kind of hard to see because it's behind the modules and trackers. And then after that, we put in our shading objects. It has a lot of shading objects, just like you would have in PVsyst. So we have the trees and power lines, and et cetera. And because you've already got the terrain in there, the objects will be placed at the correct elevation. So you don't have to think about making that terrain work. And let's see if there's, well, down on the right, you can see where the little trees have been put into the scene using that tool where you can define the parameters. And then once you have the whole scene done, then all you have to do is save it off into a PVC file that has been coordinated with PVsyst so that PVsyst already knows the parameters and how to read it. So you just have to click on a couple of buttons there and you'll have a PVC. So this is that same scene when we read it into PVcase. We didn't bother with actually the roads and so forth. We only have the actual shading portions. And so we have the trackers, modules, and those black lines are all the trees that were put in. And one thing we like about this is because this is coming from your design, the modules are already defined, the type of module you have, so the sizes are already right, and when you bring it into PVsyst, you don't have this whole having to adjust from the sensitive size to the module size. It just happens automatically. This is a close-up of a portion of that scene. Hopefully you can see the different tracker rows, and then hopefully you can also see a bit of a wiggle in there where there's some terrain. The brown is the trees. They're all very close together. But what you do notice is there's no ground in this picture. And so the heights and the relative positions are correct even without having any ground. And in terms of PVsyst, you don't actually need the ground because it's not part of the shading. You only need the shading objects. And then for the bifacial calculation, the racking height is already entered with your other bifacial parameters. So that's separate and already a known value. The fact that the shading objects come in at the right height really adds a benefit to making this in PVcase because you don't have to try to add them and put them with some elevation. Okay, so now I'm going to talk about the benchmarking work we've been doing, trying to see how the slope losses are generated by different methods. Obviously, we're trying to think about ways we can incorporate terrain effects and slope losses into our performance estimates. So I put together 5 project examples. 4 of them are actual designs that have been produced in our design team, and one of them is an idealized system with a very simple slope loss. And we're going to compare the slope losses computed from the PVcase scene directly in PVsyst to what method that we've been using, a method we developed ourselves, which also uses PVsyst, but it doesn't use the 3D scene with the slope in it. So, and then we're going to analyze the results in terms of location and weather. Just to give you a basic idea of how our existing slope loss algorithm works, we had developed this when we were doing some project work with NextTracker, and we were able to validate with some of their data. The basic method is we break down the terrain according to the direction of tilt, and so we have east tilts, west tilts, and so forth. And then we model these as multiple variants in PVsyst, and then synthesize the results using some proprietary post-processing. So it's actually a bit of work to do this because of the way we have to break it down. And so this is another big advantage of bringing in the 3D scene correctly represented. This is a summary of the scenarios. All of the systems are in the 100 megawatt range, except for we have a really big one there in the middle. Like I said, these are all real scenes, except for the fifth one. Fifth one is just a test scene we made up, and it has a 5% slope to the east and a 5% slope to the west in equal quantities. And we have 2 2Ps and 3 1P, et cetera. And the pitch is going to be important to your shading, so I've included that here. We have a range of different slope values. In the north-south slopes, I've given you those separately, but then the combined value, and if you'll notice the combined value doesn't add up to the values that you see. That's because the north slope covers a different area than the south slope, so we have to weight them according to the actual area. So you'll see when we're finished that the net slopes for the north-south directions are very small. The east-west slopes, that average is actually the average of the absolute value. So it's the overall slope where we're using the east and west slopes equally. And there is a good range in there. Again, we got from 0.78 up to 5%. There is a sixth scenario. It's the same as scenario 1. It's just that we used thin film modules because we were curious whether that made a difference. And here are the results of computing the slope loss using PV case seen in PVsyst and using our technique. Our technique is the orange one, PV case is the blue, and the slope losses are on the y-axis there. And in most cases, and the gray is the difference between them, so in most cases they're quite close. The scenario number 4 is a little bit farther off than the other ones, but actually we were fairly impressed that they would come out that similarly. So that was the basic result. That was just based on overall annual average output. So we decided to additionally look at some other factors that affect slope loss. So obviously we'd already kind of discussed terrain, and then there's the pitch and GCR, but the important thing for the slope loss is the angle at which the sun is coming in onto the panels. And so that's a function to some extent of latitude in addition to time of year. But obviously if you're at the higher latitudes, you're gonna get a lot of lower sun angles than if you're at lower latitudes. And then the other factor is the extent to which you have direct beam versus diffuse sky, because you don't get shading for the diffuse. And so we're going to look at something, we're going to look at the diffuse fraction, which is the diffuse irradiance over the GHI. So it just tells you what percentage of the incoming light is diffuse. So we're going to do some runs as a function of location and weather. And to do this, we've moved the projects around within PVsyst, which means we have exactly the same layout, exactly the same system, but we changed the site files and the Medio files. So we can just see the effect of the different angles. When we have a selection, we tried to get different latitudes and kind of east and west and different choices. So I can only show you results from a couple of the scenarios with this much information. So it's scenario 1 and scenario 3. And in this case, we're looking at the computed slope loss against on the left axis, and now as a function of latitude. And the BV method is in the orange, and the PV case method is in the blue. And we do see some differences again, but they seem to, especially in the scenario 1, they show a similar trend, where with increasing latitude, we get more slope loss, which is what we anticipated. In the scenario 3, the Black and Veatch method shows that same kind of a trend, but there's less of a trend in the PV case version. And I have to say, we don't know why at this point. These differences might pop up, but so we can conclude that the lower sun angle does increase the losses, and that the Black and Veatch method is more sensitive to sun angle than using the full PV case scene. Right, so these are the results of looking at the slope loss as a function of the diffuse or radius fraction. The diffuse fraction ran from about 30% to 45%, as shown on the x-axis. And these are the same scenarios we had before. And again, it's the slope loss on the y-axis. And in this case, you would expect that the higher the diffuse fraction, the lower the slope loss would be, because you won't get as much shading. But we don't really see that result, except in the one case with the PV case on scenario 3. So I have to assume there's more going on there. That's the latitude effect and maybe some of the other effects of the GCR, et cetera. We haven't been able to tease that out, but thought this would be an interesting exercise. Suddenly doesn't want to work. Thanks. Okay, so all of these other factors do change over time, and so it's one thing to say that we have a 3% slope loss over the course of the year. But because the diffuse fraction changes with the weather and the height of the sun changes over the course of the year, you could expect the results to vary. So in this case, the diffuse fraction is shown in the background in the solid form, and that's on the right axis, and then the losses are on the left, and the colors are the same as before. So again, we would expect that when the sun is lower, you would have higher slope losses than in the summertime. And the diffuse fraction would also generally, most places would increase in the wintertime. Mostly you have more clouds. And we only see a kind of a hint of that behavior, like on the left side of the scenario 3, where it's going down and then flat. But it was interesting to see, though, that essentially the two methods track each other, and they have reasonable correlations which are not shown. So I can't tell you what they are, but they do track up and down together, so there's something, you know, real going on over the course of the year. So to summarize, these are the advantages and disadvantages that we found when working with PVcase. One of the main advantages was that we were already using it, and I think quite a few other design teams are using it for the layout of their modules and racking. It's easy to create the complex slope scenes. You just say, read in the terrain, and it puts in the terrain, and the racking conforms to it. As I mentioned before, the shading objects will be put in at the proper heights. And because of some coordination that they did with PVsyst, the files work well together. And the results that we've seen have been consistent with our expectations. The disadvantages, at least from the point of view of the user, are that you have to have CAD software because it's only a front end. And the performance teams, like our team, we don't have that. We don't run CAD. So it's an expense for us. But the design team does. And so for us to just ask them, could you put the terrain on there and give us that instead of giving us a PDF so we can make our PVsyst scene, it's not a big deal. So we can work out that. Another issue is that it creates many objects, many objects, especially if you have a big array, because it's putting in all those individual trackers, where in PVsyst you might put in a block at one time with, you know, it could even be fairly big. Every single one comes in separately, and the way we're doing it, every single tree comes in separately. And the case that I just showed you has like 9,000 objects in it, which can kind of gum up your PVsyst calculations. And then finally, there are some limitations in PVsyst treatment of 3D scenes, which I guess were not really discussed, but particularly for the backside production, there's still assumptions made that don't actually include the terrain. So there's still progress that could be made in improving the modeling using the scene, but in general, it's been really helpful to us, and I think we might go in this direction. So thank you very much.